Let's wait maybe for 2 minutes and then we can start. Are your friends expected or are we going to have low attendance today? Welcome. Okay. Has not been announced yet. Your DSP exam is going to be on Tuesday, as far as I know. I don't know if it's the first session or the first exam or the second exam on Tuesday. Okay, we'll get started because we have a few things to cover today. Any questions from yesterday or from Monday? So let us quickly review what we did on Monday. So the main thing that we did was we defined what? The Z transform. Right? Do you recall the definition? Right? This was the definition that we had. And we also motivated this, right? Do you recall why we wanted to talk about the Z transform when we had already defined the Fourier transform, the discrete time Fourier transform? We gave a few examples, or we motivated this, right? Why do we want to work with such a transform when we already have the DTFT where we have e to the minus j omega n? Right? Do you recall why we said we want to go with the Z transform? Why? Why is that? Now, towards the end of the class last week, we discussed some of the shortcomings of the DTFT, right? We said that if we want to accommodate certain types of signals, then we will have to extend the definition of the DTFT so it can handle signals that are, say, not absolutely summable or square summable, right? And in yesterday's discussion, on Monday's discussion, we said that if my Z is actually r e to the j omega, right, then we found that this r is going to help us, right, because it's going to help us with sequences that may not, for which the DTFT may not exist, right? And depending on the value of r, we can actually try to find regions in the Z plane where such input signals or systems are going to converge, right, because of the r that we had there, right? And we also defined what was known as the region of convergence, correct? Do you recall what we said was the region of convergence? Right, so we have this summation, right? Now for the summation to exist, we put down some conditions on the region in the Z plane where actually this thing would actually sum to something finite, right? And we said that for all the values of Z in the Z plane where that summation actually exists and is finite, that is what we defined to be the region of convergence, if you recall from our discussion on Monday, right? So are you clear about this distinction between the Z transform and the DTFT? Why we want to go with the Z transform? And we also showed something else also in class, right? Is this an eigenfunction for LTI systems? When I have an input signal like this, when I raise this to the n, right? When that is my input signal to an LTI system, is that, did we show, was that an eigenfunction to LTI systems or not? Right? So that is another motivation for us to be looking at the Z transform, right? So it gives us a better way to represent signals and systems. Okay? Any questions so far? Okay? So let me ask you one question then. So yesterday, with a couple of examples that we saw, if I simply gave you that, am I specifying the Z transform of a signal to you? Why not? Right. So I need to additionally specify where actually this exists, right? Where this is defined. So for example, in yesterday's class, we saw two sequences, right? That had the same poles and zeros. So what are the poles in this system? Z equal to A is a pole, right? And where do we have a zero? We have a zero when, right? Even if I gave you this information, that is not going to specify the system for me, right? I need to say for which region in the Z plane this exists, right? Say if I did that, do you recall what the input sequence was for us to get this Z transform? Right. So this correct? And when I said, so suppose instead of this, I gave the condition, in that case, what sequence would I have? Right? Do you all recall this from Monday? Okay. And we qualified this as what type of sequence? A right-sided sequence, right? Because we have u of n, which is essentially going to multiply my a of n. So this sequence is going to be 0 for n less than 0, right? And this is kind of the mirror image of that, except that we will not have the function defined, I mean the function is going to be 0 or the signal is going to be 0 at n is 0, right? Okay, so let's continue from this point onwards. So far clear? Motivated why we are doing this, right? We want to be able to analyze the properties of signals and systems in a slightly more generic framework, and we also kind of try to say that this is the equivalent of the Laplace transform from the continuous time domain, right? I think we mentioned that also in class on Monday. Okay. Any questions at this point? No? Okay. Then let's continue. I want to cover a few things today before your midterm. Let's see how far we can get. Okay, now let's look at this example here. I'm telling you that my x of n is okay. So what would be the Z transform of this? Okay. So this is again in this form, right? A to the n u of n, correct? Both these signals are in that form. right? So what would be the Z transform here? Okay, and we have to be careful, right? This is for the case, this is right, and if we do the same thing here, this is for the case correct, and this thing goes here. Now I want to specify the ROC such that this is true for, yes, for both cases, right? So when will it, so what does this imply? This implies that my right. So which is the bigger circle of these two? This thing, right? So it means that if my Z satisfies this condition, it's automatically going to satisfy this condition, right? Is that clear? Right? So it means that my region of convergence is going to be Z greater than 1/2. Is that clear? Why this is the case? Right? Okay. So the one of the key takeaways from this is that the ROC, when I have a combination of sequences, or when I have a linear combination of sequences like this, is going to be the intersection of the ROCs for each of the individual sequences that are present in my signal. Okay. So if I were to just plot this out, right, how is that going to look like? So in this case, I have a pole at Z is 1/2, right? And I have a pole at right. So if I were to plot just the ROC for this guy, it means that my Z has to be greater than 1/3, right? So that's going to be okay. Now if I were to plot the ROC for this guy, it's going to be outside here, right? Right. So what is going to be the intersection of these two ROCs? Essentially the checker pattern, right, or the plus pattern, right? So this region here, yeah, essentially the region that's sitting out here, right? Because this must be true for the most general case, or for the case where it satisfies for all the component sequences that are present in my signal. Okay, is that clear? Okay. Now just so this is completely clear, let's look at another example to show you this intersection idea of the ROCs. So let me write it here. Okay. So what is the next example we have? X of n. Again, here we have a linear combination of a right-sided sequence and a left-sided sequence. correct? So which is the right sided sequence here? This one, right? And which is the left sided sequence? The other term, right? Okay. So if we look at just this thing here, based on our analysis so far, what is going to be the Z transform just for this guy along with the ROC? And for the condition, right? Now what is the Z transform for this signal? Again, looking back at our example. For the case do you recall the expression that we had for the left-sided sequence? So it's essentially okay. We have okay. So here we have okay. So this is going to be plus here, and that's right. Okay, and the condition is you said right? Or it's less than right? Say that again. Okay. Even for this left-sided sequence, yes. Okay. Okay, but this is the region of convergence, right? So we have these two conditions here. Okay. So now if we draw out the ROC for this thing, how is it going to look like? So this is 1/3. So at what point do we have a pole here? Minus 1/3, right? And where do we have a pole in this case? At 1/2, right? Plus 1/2. Just so we are all on the same page, what is a pole? Yeah, what is a pole? So when this is going to become infinity, right? It's not, so when the denominator is going to go to 0. The z at which the denominator is going to go to 0, that's called the pole of this x of z, right? Okay, so we have a pole here, and so the ROC for this thing is outside here, right? And the ROC for this is inside this circle, right? So this is going to be so now is there a region here that satisfies both the conditions? Right. So essentially this disk here, right, which has the plus shading over there, right? So the point is that when you have such linear combinations, the ROC is going to be the intersection of the ROCs for the individual sequences in that signal. Okay, that's the key takeaway from here, right? Clear? Any questions? Clear to all? Okay, if it's clear, then we'll quickly proceed. Any questions? Okay. So this check is clear, right? This, we are trying to do the summation. I just erased the Z transform. We have the summation of this thing. So just so it's clear to everyone again, it's 1 by 2 into Z inverse. I'm just taking the Z transform of this thing here. And for this to be able to converge, we want the magnitude of this term here to be less than 1, right? So this will be equal to is it greater? Yes. Okay, one more question for all of you. Why are these things circles? Right? Okay. And so if you look at the condition for convergence, right, we are only interested in the magnitude or the amplitude of your complex quantity, right? And the moment you say something is complex and you're defining the amplitude or the magnitude of that, it's always going to be you're specifying essentially the radius, right? So when I pick Z equal to 1/3 in this case, it means that when I say this, so essentially what am I saying? Right, where my Z is right, and so this is going to become and that is the expression for or the equation of a circle, right? Okay, clear? Okay, let's proceed then. Okay, so now if I told you that I have a sequence like this, x of n is say n I gave you such a sequence, okay, and I'm saying that this is defined for a finite time duration, right? So is the Z transform of such a signal, is it going to exist? Okay, and where is it going to exist? What is the ROC for that? Okay, do you think this is going to have any zeros or poles? Okay, so what if we calculate it, right? Say if you want to find x of z for this, So I'm just going to go from n is 0 to n minus 1. Right? And what is that going to be? Right? This is series summation, right? Okay. And so if I simplify this, what's it going to become? Right? Right? So this is z to the n. Okay. I think what I had earlier was correct, right? Yeah, is that right or wrong? Okay. So how many poles do I have here? Okay. So now, so I have z to the n minus a to the n, right? Can I always write it out as so? Do you recall the expression for this from your 10th or 12th or? So I can always write any term like this as z minus a times a product of some other terms, right? Do you recall the expression for that? Right? So why did I do that? So a pole and a 0 are going to cancel each other out, right? So how many zeros do I now have? So I will have potentially n minus 1 unique zeros in this case, right? And how many poles do I have? And they all occur at what point? Z is 0, right? Because that's the only term that's in the denominator now, right? Is that clear? Okay. So, and what was one of the other things we said in class yesterday? Can the ROC contain a pole? No, right? From the very definition of the region of convergence, right? So at a pole we have that the summation is infinite. So in this case, what is it telling us? Apart from 0, everything else is our ROC, correct? Because it's only at 0, at z is 0, that this is going to become infinite, right? This whole thing, right? And so how is my ROC going to look like for this case? So I have a pole here, right? And it's essentially going to be the whole region outside of that. Right? And I'm going to have a bunch of zeros, right? Corresponding to this part of the equation here, right? Now, one other way to calculate those zeros is if I simply set this thing to 0, right? correct? And so what do I get from there? Right? And say my A is 1, right? And N is say 3. You've all seen the complex roots of unity, right? So how would they be? So if I were to use that result, then my Z is essentially going to be A e to the j my K is going to go from 0 to, right? Is that clear? This is just the complex roots of this quantity here. And just as an intuitive example, you can take A is 1 and pick any value of n, and you will find that those roots are going to lie on the unit circle, and say if n were 3, they're going to lie 120 degrees apart from each other, right? You have a root at z is 1, and then you have a root at cos of 2 pi by 3 and sine of 2 pi by 3, and then cos of 4 pi by 3 and cos of sine of 4 pi by 3, right? That's what you get when you plug A is 1 and n is 3, for example, right? So using this, so now I'm going to mark out a radius of what? A, right? And then I'm just going to just put my zeros. This may not be accurate. Say if I pick, say n is arbitrarily 16, right? One of these, for the case when k is 0, we're going to get z is equal to A, correct? So that's going to lie at this point, A. And we also have a pole at that point. So those two things are going to cancel each other out, right? When k is 0, in this case, essentially my first root, that's going to lie at z is equal to A. So the radius of this thing is A, okay? And so this is what is going to happen, right? So that is going to cancel out this pole that I have. So I will not have anything here. And the rest of the zeros are going to lie on this circle with radius A, right? And what is the angle here? 2 pi over. Okay? Is that clear? All right. So essentially the point of this example is that for finite sequences, finite duration sequences, the Z transform is always going to exist, except perhaps at Z is 0, right? So which is what is happening in our case, or when Z is possibly infinite. But otherwise it's mostly going to include the entire Z plane. Okay? Any questions? So does this also clarify the concept of the region of convergence for the Z transform? Okay? So another point I just want to reiterate is that whenever you specify the Z transform, not only should you specify this equation here, but you also must specify what? The region of convergence, right? Because without that, this becomes meaningless. And we already showed that with the example of the right-sided sequence and left-sided sequence having the same Z transform and the same set of zeros and poles. I mean, one follows from the other. But if we didn't specify the ROC clearly, then you could end up with the wrong inverse Z transform, right? Okay? Any questions? Okay. So let's proceed then. So this is done. Now let's look at the, like we did with the DTFT, we look at the Z transform of certain common signals that we encounter. Okay. So I'll do a couple here and then you can do the rest. It's kind of trivial. So what was the first signal we defined in this class? Right? If we follow the same notation, so what would be the Z transform of the delta function? 1. But are we done? So what should we specify? So the ROC is what? Is whole of Z, right? Right? The Z transform of that exists everywhere, correct? Okay. Now, what is that going to be? And what is the ROC? What is the ROC for this? And you could potentially have zeros where? Where do we have the zeros? Actually, it is the whole of Z, right? It is defined everywhere. So, right. Okay. And do we have multiple poles at that point? So we have Z to the n naught, right? Z to the n naught is 0. So we have n naught poles at that point. Right? Okay. Now let's look at something that's a little bit more interesting. Let's pick, say, so we've already done A of n, right? And what's the ROC here? And we've derived this already previously, right? Okay. So now let's look at this sequence here. So this I can write out in terms of the exponential, right? So this is equal to right? And then is it easy to simplify this thing? So what do we have ultimately in the summation? So if I want to take the Z transform of this, and my summation is going to go from okay. And do you want to simplify this? Right? Anyone wants to quickly simplify that? This is in the same form of this thing, right? So that is equal to 1/2 of 1 over 1 minus And what is the condition now that I have? Would this be the same condition for both the summations I have here? Because all I have is simply this thing, right? I have a change in the. So this means what? Right? So what does this mean? So this is the ROC. You can simplify this to bring it to a much simpler, much less cumbersome form. You can see that again there, right? So when I take the multiplication, when I take the LCM and when I do this, I have R e to the minus j, Z inverse, then I have R e to the plus j, so that's going to become again a cosine term, and you have some other things you can simplify. Okay, I'll leave that up to you to do the simplification. But again, you get the idea, right? So we should be careful when we do this summation to take care of the ROC for each of the sequences that are present in our combination signal like this. Okay, and the ROC is going to be the intersection of all those regions. Okay, of the individual ROCs. All right. So we have done that. Now, any questions at this point? Any questions? The motivation is again similar, right? We did the same thing for DTFT, where we looked at a few common signal types and then wrote out the DTFT for those things. Okay, and we are doing this the same thing for the Z transform. Okay, when we start to do system analysis, we will actually end up using all these things that we are right now preparing ourselves with. Okay, so just bear with me for probably another 2-3 classes after your midterm, where we will actually see the application of all these in a real systems analysis. Okay, I'll try to give you one more motivating example after we finish some of these things here, so that we kind of summarize what we have done so far until the midterm. Okay, there are no questions at this point. I'll continue. Okay, so the idea of ROC clear to everyone? Okay, so let me ask you, so what is the ROC? Region of convergence. And how did we find it so far? Right, so we want to find where the summation is going to exist, right, where it's going to be finite. So we want to first find the places where it's going to become infinite, and how do we find that? Typically by looking at where the denominator is going to go to 0, right, and those are the position, those z's where the denominator goes to 0, we are calling poles, right, and the places where it's going to become 0 in the numerator, we are calling as 0, right? Okay, so hopefully that is clear. Now we'll just list out some of the properties that we have discussed so far, just so it's kind of summarized in one nice table. Okay, so the ROC of a sequence is going to be a disk, right? It's going to be a circular disk, right? And we've seen that from the example so far that it most likely, or it has always been some circle, right? It's either it's bounded by a circle, or it's outside of a circle, right? Or it's bounded on the inside and outside by a circle, right? And we gave the reason for that, right? What is the reason for that? Why are we always going to be looking at ROCs that have some circle involved in it? Because we are dealing with complex magnitudes, right? And when the moment we specify the magnitude of a complex number, we are specifying actually a circle, right? So that is the first observation that we have made. The ROC is going to be So typically what we mean by that is, so we have the region RL. So this could potentially be 0 and this could potentially be infinity, right? So we could have the ROC span the entire Z plane. Okay, so that's the first observation. Then the next observation is the relation to the DTFT. So we all recall the relation between the Z transform and the DTFT, right? So when I choose my R to be 1, I essentially go back to the DTFT, right? So if the ROC of a sequence contains the unit circle, it means that for such a signal, the DTFT exists, right? Now, what was the observation we made about the poles and the ROC? Right, the ROC doesn't contain poles, right? So that's the third observation that we've made. Okay. Now the fourth observation that we made was the example of the finite length sequence that we considered, right? So what did we conclude about the ROC for a finite length sequence? Yeah, so it essentially is going to contain right? We saw that also for one case, right? Okay. So we're done with 4. The next, yes. Sorry? It can contain, because it means that the sum is just 0 at that point. That's all. Right. So we saw in that case, right? So we had 1 over that term. So this is going to become infinite at z is 0, right? So that's what I mean. So it's mostly going to contain the entire Z plane, with the possible exception of just these 2 points. In a few cases. Okay. What was the next thing? Yeah. So when we looked at right-sided sequences, so what was the conclusion we drew about the ROC of a right-sided sequence? Yes. So we said that the ROC is going to be outside. Can we be more specific? We just say outside a circle. Outside the what pole? Not unit circle. The largest pole, right? Because we know that it cannot contain any poles, the ROC, right? So it is going to be outside the right. So in that case, we can say and this is essentially going to correspond to the magnitude of the largest pole. Correct? Okay. Now same thing about the ROC is going to be, right, the ROC is going to lie okay. So we've seen all this, right? We're just summarizing them in one place. Okay, so what's the seventh? So we have a two-sided sequence. We also saw a two-sided sequence, right? So what can we say about a two-sided sequence? Right? And that's a result of what property? Okay, so it essentially is a consequence of the property that the ROC, right, that's correct, but it follows from the property that the ROC of such a sequence is going to be the intersection of the ROCs of the sequences that, of the component sequences in such a two-sided sequence, right? So I can always write a two-sided sequence as a combination of a left-sided sequence and a right-sided sequence, right? So we know from the previous two results how the ROC is going to be for a left-sided sequence and a right-sided sequence, correct? And so when you take the intersection of these two, it has to be above something and lower than something, right? And it could be for certain sequences that the intersection is going to be 0. So essentially the Z transform does not exist for certain cases. So that could also be very well a possibility. So in case of two-sided sequences, the ROC is going to be I flip this around. Is that right? Okay. And we know the reason for that. All right. So there is one more property that I'm just going to mention that to you. We haven't seen that because of because we didn't want to go too advanced yet. So one other property that I'm just going to mention to you here, just for completeness. Okay. We won't try to prove this now. We'll probably prove this when we go to system analysis. This is the 0th element in the time sequence. I'm just mentioning this here for completeness. Okay. Okay, so now let's look at one example. We've looked at some of the properties now, right? Let's try to analyze a system that's given to you like that. Okay. So what can you tell from that system that I have put on the board? Using the notation that we have followed so far. Right? 2 zeros at 0 right? And how many poles does it have? 2 poles, right? So one at -2 and one at 1/2, right? Now what are the possible ROCs we could have for such a system of poles and zeros? Okay, so we have one ROC. So number 1, right? What else? What other ROCs can we have? Second one? Okay, what was the other one you said? Okay. Can we have anything more or anything less than this? Anything more than this? No? So we have kind of exhausted the combinations that we have, right? Okay. Now, if I were to tell you that my system needs to be causal, right? Which ROC is going to satisfy that? Okay. So this is going to be a causal system because of what property of this thing here, right? For a right-sided sequence, we have that the ROC is going to be outside of the largest pole that we have, right? And this right-sided sequence means that we don't have any component of the signal that occurs when n is less than 0, right? So that is going to be a causal signal or a causal system, right? The first ROC. So now if I want an anti-causal system, again follows from the left-sided, right? Now, if I want to have a stable system, it must include the DTFT, right? So, which of these ROCs includes Z equal to 1? Third one, right? Now, can I have from this set of poles and zeros a system that is stable and causal? Yes or no? Can we? So this is stable, this is causal. I want to find out if this system is stable and causal. Yes. But can we have a system like that? If z is greater than 1 by 2, it should not include this, right? No, right? We cannot have, for this set of poles and zeros, we cannot have that this system or this signal is both stable and causal at the same time. Okay? So essentially what this is telling you is that you have this for a two-sided sequence, right? So the moment I say it's two-sided, I have a component of the signal or the system that occurs before n is 0 or when n is less than 0. And when I say that, it immediately becomes a non-causal system, right? Or a non-causal signal, correct? And it is still stable though, right? Because the ROC includes the unit circle, right? If I have this. Yes.
Greater than 2 means causal and 1 by 2 third case means
right. So we say that a signal is stable. The general definition is when the DTFT of that exists. Okay, so from the Z transform, the DTFT will exist for a given signal or a system if the region of convergence includes this unit circle. Because the unit circle corresponds to just the DTFT, right? So in this case, of these three ROCs, there's only one which encompasses the unit circle, right? So for that system, it's going to be stable here, right? And so that's going to be a two-sided system, however, or a two-sided sequence, right? And so the moment I say it's two-sided, it cannot be causal because it has components of the signal that are non-zero for n less than 0, right? And so that is why for this set of poles and zeros that I have specified here, we cannot have a system or a sequence that is simultaneously stable and causal. Okay? Yes.
On which sequence we are defining a causal and anti-causal?
Say that again.
For which system we are defining causal and anti-causal?
Yeah. So I'm specifying the ROC, right?
The causal is should be defined for a signal line from my Fourier. Is for what we were defining.
So I'm telling you that this could be the poles and zeros either of a system or of a signal.
How would this be a system? We are just representing it in a Z transform.
Okay. So what if my so I have a set of poles and zeros here, right? So how do I try to write out the equation here? So I have a pole at 1/2, I have a pole at I have something like that in the denominator, okay? And I have two poles at so if I were to define, say, let this be h of z or x of z, doesn't matter. For example, right? So if I were to specify something like this, would the poles and zeros that I have specified here, would it satisfy this h of z that I have or x of z, right? So I'm not giving you this explicitly, I'm just giving you these poles, the location of the poles and the locations of the zeros, okay? If I were to have a system like this or a signal whose Z transform is like this, with, I haven't completed that yet because I have to specify the ROCs, right? So the moment I specify my ROCs, it's going to become one of these possibilities, right? So if I have a, so now when I specify this ROC, what is going to happen? I'm specifying that my Z has to be greater than 2, right? And it means that my pole is occurring at 2, correct? So how do I go backward from that information? I have if I have a system like this, and if I now invert that, what am I going to get? Yes? I'm giving you, so first I just specified the poles and zeros, right? So we are saying there could be these ROCs. Can it be? No, but in the first case, can it simply be z less than 0, less than 2, sorry? Based on all these conditions that we have here, right? What does this impose on you? Yeah? So because of this, we have this condition here. So I'm just trying to specify just the poles and try to analyze what are all the possible combinations or possible options we have for the ROC. Okay? If it is that, if I'm saying that my ROC is Z greater than 2, then when I invert such a system, then I'm going to have something like this as my input sequence that gave me that ROC. Okay? So in this case, it turns out to be a right-sided sequence, which is nothing but a causal sequence. This could be x, h, whatever you want to call it, x of z. This could be h as well. Why not? Mm-hmm. Yes, this is a causal, that's fine. For this set of poles and zeros that I have specified here, we could have systems that are stable and causal everywhere, right? Mm-hmm.
So it will lies that left hand side. That possible that the system is stable and causal.
Yes, so what if I have a system like this, right? Is that a stable system? Right? The ROC is essentially the whole of Z. Is it a causal system? Yes.
If h of n is 0, then n less than 0. Then the system is said to be causal. Like here we are giving the input system and we are defining that for n less than 0 should not be, it need not to be 0.
Sorry?
The input need not to be 0 for the causality. The input need not be 0 for n less than 0.
Okay. No, I'm saying that if it satisfies this property, it has to be causal. If the ROC is going to be this, I'm putting a condition that if this is true, then you could have a range of signals, right? Causal, anti-causal, whatever you want. But given this set of poles and zeros that we have here, and these different conditions for the ROCs, then what happens when what happens to the input sequence, or what's the property of the input sequence or the input system when this is the ROC for it? That's what we are trying to discuss here. Is that clear? Do you have questions? Clear? Not clear? Yes.
Causality or non-causality is defined for a system.
Okay.
Sir, but here we are having information about our signal. So just by looking at signal, how can I tell about system? Like that signal can go to any system, causal system or non-causal system.
Okay. No, I'm just saying that, see, the point is we are trying to look at the Z transform, right? So it could be the Z transform of the H of n of a system.
If it is for h of n, then I can definitely say that it's causal.
Okay. Now, causality simply means that in the general sense, what we have said is for n less than 0, the system or signal has to be 0. That's all is the definition. And in the case of a system, we say that when there is no input applied, there should be no output, right? There should be a cause for an output to occur. Okay. Still not clear? You have questions? Yes.
So without defining a system, how can we define a causality?
Okay, I'm telling you that this is actually the Z transform of a system, or the poles and zeros, say assume, of a system. Okay, and yeah, why not?
Phi of n is equal to phi of z is equal
H. When I say system, I say H, right? Okay, and so when I specify the poles and the zeros like this for that system, right? Then my question is, what type of system could it be if these were the different possible ROCs I have? Right? That's the whole point of system analysis, right? I don't, maybe we can discuss offline. Okay, so let me stop at this point. I don't think we have enough time to look at the inversion. I won't ask you questions about the inversion on the exam. I just wanted to spend a few minutes trying to put everything that we've learned in class in perspective. Okay, so let's try to do some system analysis, if you may. Okay, I'm actually getting across to you through a digital system. Okay, what is that digital system that I'm using to get across to you? We have a DSP happening. We have a DSP system that is in operation right now. Yeah. Yeah, we have several systems here, but I was referring to the microphone system that I have here, right? So what I want to do for the next 10-15 minutes is to see how we can put the understanding that you have so far together in trying to look at what's happening with the speech signal that's getting across to you. Okay? So this is just so we kind of, put a bounding box on all the things that you have learned so far. Okay? Okay, let's assume, let's forget the analog to digital conversion part for now. We'll get to that at a later point. But assume that we now have a speech signal that is digitized. We have that as a part of your homework as well. But the point is that we have an input signal x of n, right? And the system that it's going through is, there is a microphone here, there's probably some conversion happening here, and it's going to that receiver over there, and from there it's going to the speakers that are located in the classroom, right? So now this x of n is my speech signal, assumed to be digitized for now, and we have a system that's processing it, and finally it's going to go out. This y of n is going to go out on the speakers, right? So firstly, what was the basic signal type that we defined? The unit sample function, right? So after digitization, my speech signal is going to be represented as a series of assuming that I speak for forever, right? If not, this is going to be limited by the duration of the class. Correct? So I have my speech signal that is being represented in terms of these unit samples, and this is the amplitude of my speech, right? So now that is going to this system, which is perhaps, let's call it an amplifier system. Okay? Now let's go back and look at all the properties that we have studied in the class for systems. We define linearity, right? So do we want our system to be linear? And let me give you an example by that. Say suppose now we are going to have like a group song for some function, right? And we have a number of people that are speaking into the same microphone, right? So at that point you have different signals, different X's that are going to be input to your system here, right? So your system should not get messed up, and what's going to enter the system is going to be a linear combination of the different voices that are present, right? So our system should not mess with that independence and the linear relationship that is present in the input itself. So our system must be linear, right? We want our system to be linear so that when I have a combination of signals that are going to hit the system, the output should still retain that linear combination, correct? So we want our system to be linear, right? Next, I want my system to be time invariant as well, right? So essentially if I speak now, pause for a few seconds and say the same thing again, you shouldn't be hearing different things on the microphone, right? Okay? So our system must be and our system must also be causal, right? Because it should not start to give an output without me saying anything, right? That would be, that would be scary in fact, right? So we want our system to be causal as well, okay? So these are some of the important properties that we have discussed about systems, right? And now, armed with your knowledge of these things, we're now able to characterize a system just like that, right? We picked up a system and we say, look, these are the attributes it should have. Correct? Does it make sense? Where we can apply what you have learned so far, right? Okay, so this is about some of the time domain properties that we have, right? Then we also discussed, we went to the frequency domain, right? I'm just trying to give you a high level overview of how we can apply what you've learned so far, right? Now, oh, I forgot one more thing. The system must be memoryless, that's fine. And it must be stable as well, right? And this is an important point that I want to mention to you. This stability is an important property that we have discussed, right? And we have discussed bounded input, bounded output stability, right? As long as my voice has a max amplitude, the output also should have some max amplitude, right? But you have also heard in some cases that the mic kind of goes off, right? I mean, you have a very high frequency signal that you hear sometimes, and that is because of feedback in the system. Okay, even though the speaker is not shouting, you sometimes hear the microphone go off, right? And you keep this point in mind because this will also be important when we look at the frequency response of the system. Okay, and most likely what is happening is that there is some sort of feedback that is making the system unstable. Okay, and this can be represented in terms of an LCCDE. So the moment I say feedback, it means that the past output is being fed back to the system in the current time instant, right? So now that's where this LCCDE kind of comes into play. For example, right? So what I'm saying here is that the current output not only depends on the current input and the past inputs, but also on the past output. And this, if I have a number that's greater than 1 sitting here, that could lead to potential instability in my system. Okay, and that is most likely the cause of you hearing the whole thing becoming unstable at times, right? That's something you've already experienced, right? And one possible explanation for that is this feedback. Okay, and so you're also familiar with these LCCDs, right? So the reason I'm again mentioning this to you is if you want to now represent a signal or a system where there is feedback, you also know how to do that now, right? You have LCCDs that you can use to represent these systems, right? So that is about the general properties of systems that we have discussed so far. Okay. Now you also had a question about why we want to do DTFT, right? And the reason for that, again in the context of this example, is say suppose that I want to have amplification, right, of a signal, because right now the energy in the signal that's just coming out of my voice box is only that much, right? And what this is doing is that it's increasing the energy in that signal, and that's why all of you are able to hear me wherever you're sitting in this classroom, right? So it should not be that if there is a female teacher that comes here and speaks, the system should respond differently, right? So what I'm trying to get at is the system should be designed in such a way that irrespective of the frequency content that is present in the input to the system, the output, at least for this particular system, should be the same, right, across the range of the frequencies that we have. Okay, so what I mean by that is ideally I should have, if I look at, so what is this? The magnitude of the DTFT of my system response, right? So based on what I told you, can you define to me how this should look like now? I want my amplifier to have the same amplification at all frequencies. Okay, so essentially if I know that the frequencies are going to be contained, at least for human beings, we know that it's going to have a max frequency and a min frequency, right? That we can also hear, right? Beyond that range, we don't care. what it is, correct? But the spectrum of speech frequencies is going to occur, say, in some minus omega naught c to omega naught c, and it should be the same in this range, right? Let me call that A, right? So have you seen this in the class? This is an ideal low pass filter, right? But in this case, the point is that this A should typically be, because we want to amplify the signal that we have, right? Okay. One more related example that now you can try to explain also, right? So how many of you have a music system at home or in the hostel? Okay. Or have you had a music system in the past? Or have you seen one? Okay. Okay. So say when you're listening to some rap, right? So there's a lot of, low frequency beats, right? And so your mom or your neighbor may come and tell you, hey, turn down the volume, right? So what you would typically do is you would maybe adjust the bass a little bit, right? So that it's not booming, right? So what are we doing in that case? Based on the knowledge that you have acquired so far in this class, when you say that you're turning down the bass, what are you doing? So bass, do you think it's high frequency or low frequency? Low frequency, right? So when I'm turning down my bass, what am I doing? I am actually changing the system response so that frequencies in the low frequency range, signals in the low frequency range are going to be attenuated, right? So how will that modify this here? So I'm perhaps trying to do something like that, right? And you should be able to explain this based on, oops, I think they don't like what I'm talking about, okay. So, yeah, so coming back to this, right? So now, equipped with the knowledge you have in this class, if I now want you to design an equalizer, right, that's going to attenuate certain frequencies in the signal, right? Do you think you at least can attempt to go to the frequency domain and sketch the response for me, how it's going to look like? You think you can do that, right? So we've defined in class what high frequencies are and low frequencies are for discrete time signals, right? And more likely than not, most of the media that you have at home is discrete time, okay? So you have already equipped yourself with all this knowledge, right? And I also want, say suppose you are listening to some orchestra, right? Some Western classical orchestra where there's a lot of, musical arrangements and there's a lot of high frequencies, right? So in that case, I want to get the richest sound possible, right? So in such a case, I want to be able to make sure that I have the higher frequencies. Also, so maybe I have something like that, and then maybe I have something going like that at the higher frequencies, right? So this is something that we want to design maybe, right? We haven't seen how we are going to design these things, but the point is that you now have the tools required to express such systems in terms of equations and try to even design them. For example, if you were just to design that ideal low pass filter, right? We know what the inverse Fourier transform of the ideal low pass filter is, right? So in some sense, you do already have some system design ability already, right? Now, another last thing that I want to mention is about convolution, right? So we have defined this system now, and we want to also evaluate the output of the system to a given input, right? So I just want to just quickly mention this before I let you go. We did, if you go back to your notes, there is one example that we did about convolution, right? I defined an x of n and I defined an h of n. Can you go back and quickly look at the signals that we defined in your notes? I think it was, say just for now, let's say delta of n plus 2 delta n minus 1 plus 3 delta n minus 2, right? And my h of n is, for example, this filter, right? We have the backward differencing operation that's going on, right? So now if I were to ask you to perform this convolution, this is going to be right, and we know what the Fourier transform for the delta is and the delayed delta is, right. So you can perform this easily in the Fourier domain and invert, right. That's something also you can do. So the point I'm trying to make is, given a system and a signal, you can now calculate essentially the output quite efficiently. Okay. And the last example, I don't think we'll have time, is for the case for a system like this, right. I want to do the stability analysis of this system, right. So I take the Fourier transform or the Z transform of the system here, right. And we know from the pole zero analysis that we have done so far that we can try to see where the poles are for the system and the zeros are for the system, and then try to guess the stability of such a system. Okay, right. So with that, I'll stop. I wish you good luck for your exam. Okay, and hope all of you are able to Tuesday.